Hello,
Hey,
how are you?
good. How are you? I'm sorry about not getting that upload thing. I put an upload for the project. If you can, what I'd like you to do next week is do a little presentation of the project with you could do it with if you wanted to make a few slides and then show the slide deck, the slow show the app.
Okay,
Usually
sure.
we do a little presentation. We, I get it, but there's only one person. It feels a little funny to do it that way, but that's how we've always done it. So I guess um, that's how we've always done it, and I think it's always useful. It's a good exercise because preparing to present it, but you think a little, you find things that you want to change
Hmm.
when you do that. I think uh, so. That should be there. Um, I don't know if Rita or Hayden are going to show up. Let's give them just a minute or two to see if they're coming. Is there
Hmm.
anything else you wanted to talk about now before in a sense because you did everything very fast. We got through all the material for the class early. I'm sweeping back and doing one kind of motif that we didn't cover today
Oh,
that
okay.
we didn't cover in the past that I thought might be worth talking about. It's not too fancy, but might be of interest.
Okay.
Let's see. Okay, I'll give it one more minute. We'll start. Well, welcome back. This is our 15th and last lecture in the semester. Today, I was going to talk a little bit about feed-forward networks, and depending on how we do with that, I thought I might also talk a little bit about some principles of modeling, namely the idea of limiting cases. As always, I need to remind people that this is live streamed and recorded, and once I've got them edited, they're up on YouTube. So I'm going to introduce the feed-forward network, which we've talked about a little bit before. Um, we'll remind you maybe about how to translate a network into a possible set of mathematical equations, and then we'll do a few exercises on that and see how it goes. I had in the past used this as an example of how to do an analogy between hill-like functions and Boolean networks. I've hidden most of those slides, but they're in the deck. And if you're interested, we could talk about that a little bit more and I could show some of those slides. Usually this material takes 2 lectures to cover, and so I was trying to figure out what was the most important part of it. So the feed-forward network is something that you see in biology a lot, uh, usually in a little bit more complex form than this, which is you have a molecular species P1. And if it's a signal, it could be a signaling network, in which case this could, for example, be an enzyme or a phosphatase, for example. and or it could be a gene regulatory network, in which case this could be a transcription factor. And P1 affects species P3 directly, but it also affects some intermediate species P2, and P2 then affects P3. So there's a direct signal and an indirect signal. And each one of these interactions, in principle, could be excitatory or inhibitory. And you have what are called coherent feed-forward networks. P1 excites P2, excites P3, and P1 excites P3. Everything's pulling in the same direction. Or you could have inhibition, but pairs of inhibitors that cancel each other out, or signal inhibitors that don't. So, for example, if P1 inhibits P2 and P2 inhibits P3, then P1 is a net inhibitor of P3. And if P1 then inhibits P3 directly, they're both the direct and indirect pathways are working in the same direction. In the same way, P1 activates P2, which inhibits P3. P1 inhibits P3 directly. They're working in the same direction. Or P1 it activates P3. P1 inhibits P2, but P2 inhibits P3. That means increasing P1 decreases P2, which increases P3. So it's net activation. So these are called coherent feed-forward loops. You see those quite a bit. You also see what are called incoherent feed-forward loops, which are a little bit more interesting, at least to ask the question why they exist. In this case, P1 activates P3. It also activates P2, but P2 inhibits P3. So the direct channel is excitatory, the indirect channel is inhibitory. Or you could have it go the other way. Here, the direct channel is inhibitory and the indirect channel is excitatory. And some of these are more common than others, but if you look through enough gene regulatory networks or signaling networks, you will find examples of all of these, sometimes with additional branches, sometimes with additional layers. But you can ask why functionally these might exist as structures. And Herbert in the textbook spends quite a bit of time looking at these. Here we're going to just spend 1 hour or 2 looking at them together. And so what are the kinds of questions that you could ask? Well, the first one is if I change P1, what happens to the concentration of P2 and P3 in time? What happens to the equilibrium levels of P2 and P3 as a function of P1, as a function of key parameters? How long does the system take to reach an equilibrium? In this case, we don't have any feedback, so there can't be any oscillation. This has to reach an equilibrium. But the time scales for the direct and indirect channels might be different. What happens if I have a transient change in P1? If there are different time scales for the direct and indirect channels, then the output P3 may have a funny time dependence, or interesting time dependence. And extending that, if I had a time varying input signal, what happens to the output? And also, especially for the coherent ones, is the sensitivity to noise the same when you have the direct and the indirect channels working together? So could this, for example, act to filter out noise when there's a high level of noise? So there's a standard way of doing this kind of analysis. It's not that thrilling, perhaps, by itself, but it's not a bad approach to take when you're going to analyze complex networks, whether they have feedback or not. This is essentially the simplest non-trivial network you can analyze. And so the first thing you might do is look at the individual temporal dependencies and level dependencies. So I turn on P1 and ask the question, if there were no P2 to P3, just P1 activating P3, what's the temporal behavior? What's the saturations? If I have P1 activating P2 by itself, how does that behave? P2 activating P3 by itself, how does that behave? And then how especially do the levels and timescales depend on the parameters? Typically, you're going to have some things that are fast, some things that are slow, and the order in which things happen matters quite a bit in these sorts of situations. The last thing that you always have to worry about, and we talked about this some weeks ago, and I'll reference it very briefly, is if you have two signals coming in at P3, you have to make a decision about how they combine. Do they add? Do they multiply? Do they do something else? To remind you, we're starting out with this very abstract notation. P1 does something to P2. If we're thinking of this as a gene regulatory network, we imagine, for example, P1 is a transcription factor for gene P2. So we'd represent that as nothing goes to P2 at a rate depending on P1. And in reality, of course, if we have a gene, P2 would be RNA that has to be converted to messenger RNA and then translated. So there are additional stages between P1 and the protein itself. But we often neglect those here. They certainly will change the timescales over which things happen. But those delays tend to be more critical when you have feedback. Okay. And as always, when we have production of a molecular species like P2, even though it's not written in that initial lollipop diagram, we have to remember that P2 decays, and so we have to include the decay kinetics as well. Right. So this figure decided not to display. I wonder it was all right before. I apologize. The figure that is being deleted is this one. P1 activates gene promoting P2 decay. I'm not sure why PowerPoint does that sometimes. It showed fine on my screen a few minutes ago. I think it's a memory leak problem in PowerPoint. So the first thing that we can do, just as a review, is remind ourselves how to write a Hill function of this. And so we're going to start out with P1 promotes P2. And now we want to write a Hill function for the production of P2 as a function of the amount of P1. And so if you can remind yourself how to write the rate laws here for P2 as a function of P1. I'll just let you spend a time. And then ideally, you want to be able to find the steady state for P2 star, given the law you wrote down. And do you remember how we did that? We've done that a few times over the past few weeks. So let me know when you, or if you have any questions, or if you've got that done.
Okay. But I don't have pens or papers by my hand right now.
Well, I guess if you have your, are you on a cell phone or are you on your computer?
Oh yeah, computer. I'm using computer.
Okay, so if you can launch a notebook, you could type the antimony string implements this.
Okay.
So you'd have one rate law, which is nothing goes to P2 with a Hill function rate, depending on P1. And then P2 goes to nothing as the second line. We're going to do a little bit of computing in a few minutes, so might as well have that working. In this case, you can actually do a little bit of analytics, which is why, which I can show you. We don't have to do the derivations, but if you remember, basically, we say that the rate of production, V1, is basal transcription rate plus a Hill function of P1, and then we'll assume first order decay kinetics for P2. So in that case, the steady state will be just the rate of production, B1 plus et cetera, divided by K2, KD2 is the steady state.
Mm-hmm.
All right. So this is what, if we write this a little bit, and I did something in the past, which I remember we presented before, which is it's convenient to rescale things so that the decay rate, um, which really sets the time scale of the problem, the decay rate is represented separately. So instead of writing Vmax here, you write Vmax is equal to the decay rate, KD2, times some other rate constant K. Now, when you do that, and you rescale also C1 by that, then you basically can rescale time and pull everything, write everything in terms of the decay time. And that makes things a little bit easier to do the analysis. But the steady state, then, when you write it that way, is just the basal production rate plus the production rate times the Hill function. The advantage of writing it this way is if I change the decay rate, the steady state doesn't change. All right. And Hill functions, of course, are sigmoids. If the exponent of the Hill function is large, we essentially have a switch, a Boolean switch. K1 is the half maximal concentration. And n equals 8 is fairly steep, but certainly not completely switch-like. There's certainly some scaling behavior in the middle. And we can do the same thing for inhibition. Not going to walk through all the details. Again, you write the rate of production here. The only thing that changes is that in the numerator of the rate of production, instead of being proportional to P1 to the n, you're proportional to K1, the Hill function, to the n. And again, you rescale everything by the rate of decay. You get a decreasing sigmoid. Again, the value of P star is half when you're at K1. And for an n equal 8, you get a sigmoid that looks like this. N equals 4 is pretty smooth. It's not quite linear, but almost. N equals 20 would give you a step function. Now, as I mentioned, I'm not going to talk too much about thinking about these things as Boolean operators. There are, in fact, theoretical approaches which actually do treat all of these interactions as pure Boolean operators, where you essentially start with the inputs. You suppose P1 activates P2. You'd say at time 0, P1 has a value of 1. And then at time 1, you would say P2 would have a value of 1. Or if P1 had a value of 0 at time 1, then P2 would have a value of 0 at time 2. Or for the inhibitor, if P1 goes from 0 to 1, P2 goes from 1 to 0. And sometimes it's useful to think about these things in terms of the Boolean limit. In the case of a simple feed-forward network, the results are fairly trivial. For networks with feedback, you could get things like oscillations. And so these kind of Boolean approaches are used quite a bit. They're also used because they're fast. Computationally calculating these networks as Booleans is very fast, and you don't need to know the kinetic constants. Here we need to know at least the Michaelis K. We need to know the rate constant, the basal rate of transcription. So we need 3 constants to describe the sigmoid, 4 including the exponent. If we have the Boolean approximation has no constants associated with it. And so in the absence of the ability to measure those things, we are better off accepting our ignorance and using the Boolean approximation. Now, if we think about these things purely from a Boolean or logical point of view, then activator followed by activator is equivalent to activator. If I increase P1, I increase P2. Increasing P2 increases P3. That means increasing P1 increases P3. If I increase P1, it decreases P2. Decreasing P2 increases P3. Therefore, increasing P1 increases P3. Here, increasing P1 increases P2. Increasing P2 decreases P3. So increasing P1 decreases P3. Increasing P1 decreases P2. Decreasing P2 decreases P3. So increasing P1 decreases P3. So functionally, from a Boolean point of view, P1 followed by P2 activator is equivalent to P1 directly activating P3. But the temporal behaviors of these are not the same, and the threshold behaviors aren't the same. And for sigmoids, which are not perfect step functions, these results can be quite different as well. So in particular, in a Hill function, the key thing you need to know is the input below or above that Michaelis K? If the input is below the Michaelis K, effectively you have small input. For an increasing Hill function, your output is small. For a decreasing Hill function, your output is large. If P1 is above the Michaelis K, then for an increasing Hill function, your output is high. Decreasing Hill function, your output is low. And so the key question for these stacked circuits is, if I have P1 exciting P2 and P2 exciting P3, the key question is, at what time does P2 cross that Michaelis threshold for P3, or does it in fact do it at all? And so we could do that a little bit by looking at the time series. The first thing we're going to do is just look at our single P1 excites P2, and we get something that looks like this. P1 divided by K1 P1 to the N here is basically just a constant because P1 isn't changing. And so this is essentially dP2 dt is a constant minus K2 KD2 times P2, which is just exponential relaxation. And so what we would want to know if we're going to connect this to something else is at what time does the value of P2 reach K? So the first thing we'll do is we'll say that the solution to this equation is P2 as a function of time is P2 star, whatever that is, equilibrium steady state, plus an exponential. And the time scale, the only time scale we have left in this problem is KD2, the decay time. That's why we rescale everything by the decay time. So we know that P2 is equal to P2 star times 1 minus e to the minus KD2 t. And here I'm just showing the exponential, which I don't think I need to show for you. So that gives us our result here. And now we can ask a slightly different question, which is, we want to know when the value of P2 crosses K2. When does the second part of our circuit turn on or off in response to the first part? And so now I set K2 equal to the output of my first circuit. And if K2 is too big, well, I'm never going to reach that threshold. So I have to have K2 be small enough that my equilibrium steady state is above that. And I solve for that equilibration time. And I can do that. And I get that the equilibration time is equal to 1 over KD2, everything's in units of the decay time, times the logarithm of K2, the target, minus P2 star, the steady state value of P2, divided by the initial value of P2, normally that'll be 0, minus that steady state again. So we get that. And again, P2 of 0 is normally 0 in this case. And now you'll notice that if K2 is half of the equilibrium value, or small compared to the equilibrium value, we reach the value quite quickly. If K2 is bigger than the equilibrium value, we never reach it. And so there's a regime when K2 gets to be close to P2 star, where it takes a very long time to equilibrate. And so we can actually do a little bit of math. And I may skip through this pretty fast, but we can do a little bit of mathematics to approximate what this time is. And maybe actually, why don't I actually ask you to do that? It only takes probably a few minutes to do it. So write a little parameter scan, which is the following. Start with your simple differential equation for P2. From here, and then plot how long it takes to reach a target, your value P2 takes to reach your target value K2, um, as you change K2. And you could set K1, KD2 equal to 1. Um, that makes things a little bit easier because then P2 1 star is P2 star is 1. Does that make sense? That's a little
Yeah.
exercise.
Yeah, I can do that, but I don't have the code, so I need to write it from scratch.
Um, so you don't have one of the parameter scans that we had from before?
Uh, I don't have the code for this one, this model.
Oh, well, the code for this model is just this one. You could write it as an ODE or two reactions. Uh, Nothing goes to P2 at a rate K1, KD2, P1 to the n over K1 to the n plus P1 to the n. And P2 goes to nothing at a rate KD2 times P2. So the antimony is very simple.
Oh, okay.
That's why I wanted you to try the to write the equation first. Just write it out in antimony. So why not take a minute? I'll leave it on this screen here
Okay.
and let you so you could see the equations. And then why don't you try writing a code? I do have I have to find which folder they're in, but there is in fact code online to do this. It's not in a Jupyter notebook, but I have the Python for it. But it take 5 minutes to do it. It's not gonna it shouldn't take too long. If it does, let me know and I'll be happy to help out.
Okay, so P1 is a constant or
Right. So you're going to give it a constant value of P1.
okay, sure.
And so and then P2 will be an increasing function in time.
Okay.
And normally you would just plot P2 versus time. But what we're trying to do is calculate the time at which P2 reaches some target K2.
Okay.
So you'll run the simulation. You'll find the time at which P2 achieves whatever your target value. Uh, you could do that in a variety of ways. You could run the simulation, save the time series, and then search through the time series for the time at which you reach the target value. That would be one way to do it. Or you could run it forward and stop the simulation when it reaches the target value. Probably running it once and saving it and then finding when it reaches the target is the fastest. Because then you can change the target and see what the time does. You may want to look up how to do parameter scans if you need the code from previous class.
Yeah, I can do the parameter scan, but I'm getting some weird result.
Okay, do you want to show
Yeah,
what you
yeah,
got?
yeah, sure. You have to agree the application.
I just gave you permission to try again. There you go.
Okay, sure.
Sorry about that, but they seem to be making the security more and more tight on Zoom.
Mm.
He says, okay. Okay.
I-
So
Is this correct? I think it.
so let's see. K1 times KD2, P1 to the PX, K1, okay. Yeah, that looks fine. Line at 6. You need to
Uh,
multiply by P2.
oh yeah, right.
The rate law has to be multiplied by
That's
P2.
right.
There we go.
Now it's correct.
Okay, so now, right, P1 goes up and saturates. That's fine. I'm sorry, P2 saturates. That's fine.
Now it's okay.
Yeah, there we go. So now what you want to do is you want to ask the question, at what time does P2 reach some target value? So if you go to the output where you have result equals r dot simulate,
Mhm.
now you can use one of the numpy or scipy functions to find the value of t, the first column, at which the value is the target in the second column.
This should do it. Okay. The x-axis is not correct, but I think this figure is enough to show the trend.
Okay. let's take a look. There are a number of different ways you could do this. Let's see what I got, and then we can come back to it for a sec.
Okay.
Um, so here's what I got. So here is the value of P1. Uh, the bigger, if P1 is too small, nothing happens. Um, and here's the time it takes to reach here a value of zero point 0.1, value 0.3, 0.5, 0.71. So uh, clearly, if K2 is small, the time to equilibration is roughly linear in K2. If K2 gets very close to that saturation value, then the time to converge goes to infinity. And I'm actually puzzled here because this axis here looks, here I have P1 increasing and the time to convergence is slower. So that actually makes sense. So as I say, there are some different ways to do it. We can get a rough estimate. The equilibration time, as I said, is 1 over the decay rate times the logarithm of P2 star, that equilibrium value, minus the initial value of P2, which normally would be 0 for us, divided by P2 star minus the K2. So if P2 star equals K2, in other words, if I'm at this tangent point, then it takes forever. So the thing diverges. If P2 star is much smaller than K2, then effectively this P2 doesn't matter, and I have P2 over K2. And now I'm going to assume that the argument of my logarithm is is 1 minus x. It's near 1. In which case I could replace the logarithm by minus x. And so the equilibration time then is roughly for small values of K2, K2 divided by KD2 times P star. That would be the linear regime I think you're looking at there. If I want to go on the other limit, I can do it. T equilibrium is approximately K2 over Vmax, 1 plus K1 over P1 to the end. So I don't think we really have to do all of those things out. Uh, what I did write actually some code where the blue line here is the exact let's see, is that right? Which way is it? Yeah, the blue line is the exact result, and the orange line is the approximation. They're not great approximations. All right. So now let's actually do something a little bit more interesting. Let's write the simple stacked circuit. P1 excites P2 using the code that you have, and then duplicate that and have P2 control P3 in the same way. And now start out with, you could start out with P1 equal to some value, or you could turn it on at some small time after 0. And then watch P2 come up and then P3 come up. Now what you should see is that P2 turns on first, and then P3 turns on later. And so there's a delay. P3 happens late, turns on later than P2. So why don't you just write this little time series uh, plot where you plot the value of P2 and the value of P3 as a function of time. and see what the temporal relationship between P2 and P3 is. So is that a clear, simple, clear assignment? So
Yes.
you already were plotting P1, P2 versus time. Now you have to have circuit hitch P2 into the circuit to
Mhm.
make P.
Okay, I got some result. I haven't done the parameter scan yet because I don't know the.
Yeah, you don't need a parameter scan here. It's just to reproduce that figure that we have. So let's take a quick look. So just plot the time series for P2 and P3.
Yeah, I just randomly chose some parameters.
Okay. I suggested here K1 equals 1, the capital K equal to a half, but let's just see what you got.
It's in the chat.
Oh, okay. Okay.
This fig in this figure, the K capital K1 is 1. And when I set
Right.
the capital K1 as 0.5, I got the I think it's roughly the same as the figure you in your slide.
Okay. Let's take a look at that one because for the one that you have here, P2 never crosses K, and so P3 never turns on.
Mhm.
So actually, the example that you've given is quite interesting because in this case, you have an activator. P1 activates P2, P2 activates P3, but P2 never turns on strongly enough to turn on P3.
Mhm.
So that's that one. And let's look at the other one. Right. So in the other one, you have P2 turns on, and then it turns on P3, and there isn't a big delay, but you'll notice P3 goes on just a little bit later, maybe in your case, about one half, whatever the time units are here, it takes a little bit longer for P3 to turn on than P2. Okay, great. Okay, let's see, back to it. Am I sharing the PowerPoint now? Because I know sometimes in the past I've managed to fail to share the PowerPoint, so I want to make sure you can see it. Okay, all right. You got the PowerPoint back?
Yes, yes.
Okay, good. Okay, good. So effectively now we could say that it takes this TP2 time for P2 to reach the threshold to start turning on P3. And so then TP2 is approximately whenever you start, whenever you turn on T1, about log 2 over KD2. And then P3 is that time plus log 2 over KD3, whatever the decay rate for the other one is. And so now I can actually control the time at which P2 turns on and the time at which P3 turns on. Now to go further than this, I have to combine my signals, my direct and indirect signals. And the simplest things to do are ands and ors. This is again a review. Um, we want our output range to stay in the same 0 to 1 range that we have for inputs. And for an and, we want our output to be bigger than K, only capital K, only if both of our inputs are bigger than capital K. For our OR, we want our output to be bigger than capital K if either one is. And there are a couple of biologically different kinds of promoters that are possible. For the AND, you can have a situation where you need both A and B to bind. In that case, you typically have something where you have a product of the two hill functions independently. That will work for that if everything is scaled to 1. You get something that looks like this then, where if you change x1, you get output that looks like that as a function of x2. You'll notice in this case that the thresholds for both x1 and x2 are at a half, because I set my k to be a half. But the maximum output depends. I get a sigmoid as a function of x1, but the maximum output depends on the value of x2. For ORs, things are a little bit more complicated. Just adding doesn't work. We have either what I would call competitive or non-competitive binding. In competitive binding, we have a single activation site. And so effectively, the promoter P3 is effectively P1 plus P2. In non-competitive binding, we have a single site which could bind to either P1 or P2. They behave independently. If we want to have the competitive binding, we have a single target site. Then we replace X with the sum of P1 and P2, put it inside the Hill function, like that. And that will give us something that looks like this. As a function of x1, if x1 is big enough, I'm always output is 1. But the threshold, the effective k for x1, goes down as the value of x2 goes up. For the non-competitive case, here I have two binding sites. If I bind to one, I turn on. If I bind to the other one, I turn on. In that case, it behaves like x1 to the n plus x2 to the n over 0.5 plus x1 to the n plus x2 to the n. And that has a circuit that looks like this. In this case, the threshold value for x1 is always a half. The max is always 1. But for small values of x1, my minimum rate depends on x2. And so those are both a little bit different in terms of the way they work. Now, all of these things are compatible with each other if I assume that the capital K's are all the same. Biologically, it's often not the case that the K's are the same. Some things might have units of nanomolars, some things might be micromolars or picomolars. And that means that if I'm going to combine things in circuits, writing them the way I did here, where the K is written out x to the n over k to the n plus x to the n, doesn't work. I can't combine things. And so I always want to scale all of my concentrations by their half maximal value. And so I'd rewrite my function in the form P1 divided by 2K1, P2 divided by 2K2, and so on. If I always normalize x P1 by K1, P2 by K2, P3 by K3, and so on, and if I pick 2 times that K and use 1/2 here, then everything is scaled. All the rescaled values are between 0 and 1. And then I can combine freely. It's like digital logic for computers. If you say that a 0 is 0 volts and a 1 is 5 volts, then you can combine everything together. Or if it was CMOS in the old days, it was a minus voltage. But you want to make sure that everything can be interconnected. So remembering to divide your concentrations by their Ks allows you to do that. So again, we had that competitive OR. Looks a little bit more complicated if we put the rescaled forms in. But that means, for example, if we had P3, P4, and P5, we know exactly what we'd do. We'd have P1 over 2K1 plus P2 over 2K2 plus P3 over P2K3, PK3, and so on. So this allows us to do more complicated circuits. All right. So just to remember, for an AND, we do a product. AND circuit looks like this. A non-competitive OR basically looks like the AND flipped inverted. And now, if we have some idea of how to combine our direct and indirect signals, we can now begin to do these feed-forward networks with two direct and indirect paths. And what we want to do is ask, can we design these feed-forward networks so that they do something useful? And in particular, we want them to have particular temporal behaviors that are of interest. And so the gene circuit here is a pretty simple one. P1 directly turns on the production of P2. P1 turns on the production of P3. Um, sorry, I got that. I said that back. I said it correctly, but it wasn't what I wanted to say. P1 turns on P2. P2 does something to P3. P1 does something to P3. So we have the direct path P1 to P3, the indirect path via P2. And now we have to, for each of these cases, we could ask the question, how does the equilibrium steady state value of P3 depend on value of P1? And in this case, if we're going to, we can use the notation K AB, a K sub AB. So K13 would be the direct K from P1 to P3. K12 would be the P1 to P2. K23 would be P2 to P3. So we have that notation. And in each case, we have to think about what happens if these two signals, the P2 and P1 signals at P3, combine as an AND or an OR. So there are a bunch of possibilities. We have 8 circuits. We have 3 different ways of doing the combination. So there are in principle quite a few possibilities. So let's try the first one that's interesting, and probably the most interesting of them, which is the incoherent feed-forward network of type 1, where P1 excites P2, P2 inhibits P3, P1 excites P3. So why don't you write this circuit in Antimony? And here are some suggested values of parameters from Herbert. And notice that it uses a very high Hill exponent of 40 in this case. And all the parameters are given here. And then start with P1 equal to 0. At some time, you can use an event to turn P1 on, and then plot the time series for P2 and P3. Okay?
Okay.
And there's a hint at the end of the slide about what you might expect the temporal behavior to be.
How long should I simulate?
Well, you have to simulate long enough that the system has reached equilibrium. If you simulate too long, you won't see anything happen. If you simulate too short an amount of time, you'll see P1 will start activating P2, but nothing else will happen. So again, if you want to screen share it, I can walk you through it. But essentially, if you look at this, if you look at what's on the screen now, it has KD2 equal to 0.01. That means the typical time scale for things to happen is 100 time units. So
Okay.
simulating for 500 time units is probably about right. But if you've got the simulation working right, you'll know how long you have to simulate it for. It's very clear.
Yeah, I can share the screen,
Okay.
but I don't see the piles.
Okay, let's take a look.
Yeah. So the code is right, I think.
Okay, so let's just see what happens to P1 and P2 and P3. Let's plot. Let's see the time series. Okay, so one thing that's happening here is that P3 is never turning on. Let's try running it for a little longer. Run it for 200 time steps.
Yeah.
Hmm. So P3 is never turning on. So let's see what the rules are for P3. Um, P1 is big, so P1 should be turning on P3 directly.
Oh, wait, this one should be P1, not A. P1 is um,
Okay, so
I.
you see P1 turns on, and now P2 comes up, but P3 is not turning on, even though P2 is off. So let's see why is that. Um, you have an activator. Let's see. You have P3 depends on activation of so you don't have an inhibitory signal for P from P2 to P3. So if you look in line 10, you have P2 there, that's activating, and P3. So you have all of the circuits being green. So you want to replace P2 to the n by K2 to the n in the first part of that equation, K2 there. That should be K2.
Replace
Yeah.
P2 to the.
Right. You have an excitatory Hill function and you need an inhibitory Hill function. So you need a K2 there.
Oh, this, you mean this
Yes.
one?
Yes, now.
It's K2.
Now try it.
Wait, it's capital K2. There's
Yes. Yes, capital K2.
uh, there is a small pulse, I think.
Yeah, not much. I wonder why it's not doing more than that. Let's see. So Let's come back. So one thing that you have here, okay, so you have KD, let's see. You have K1 equal to K2 is 1, that's fine. You have the decay constant KD2 0.01, so it's slow. You have decay constant KD 3.2, that looks all right. All right, so those all look okay to me. What is not working? Let's see. And I noticed that I have a typo in the slide, so let me fix that while I'm looking at it. So let's look at your simulation again. Let's run it. They run the time series again. Let's take a look at it. All right. So you see, I'm just looking at my output and seeing what's happening here. You see P2 turns on and P3 starts to turn on, but we never get uh, um, we never get it to be excitatory. Why not? Let's see. So P3, so P2 is behaving the way we expect it to. And so the question is, why is P3 not behaving the way we expect it to? P3 should be turning on. So let's start out by just copy line 10 and let's have just the direct excitation. So now yeah, and now so get rid of the inhibitory Hill function, the first term there. Yeah, 1. Yeah, okay. Now let's run it and see if P3 turns on. So P3 is still not turning on, which means that our issue here, our issue here is in line 11, where we have KD2. That has to be KD3 because it has to match the decay. That's what the problem is. Now let's try turning it on. So now P3 turns on fast. Okay. And now do the same. Now undo that one, but we have to fix that. Yeah. Okay. Now put 10 back. There we go.
Ah,
There you go. Now you got it. Now there's still an issue, which is I don't understand why um, it's turning off. It's turning off when P2 is only at 0.2. So why is that? Let's look at that. So where is the P2? K2, capital K2 is 0.5. K3 to the N. And what do we have as the value for K2? 1. So that actually looks okay. Let me see. I'm just looking because I have effectively the same. I have effectively the same time course, but my value of K of P3 is going up to 1. And so I'm not sure why the value of P3 is not going up to 1. Let's see what's happening here. If I have KD3 times P1, okay, so there's an extra KD3. That's what's happening. So in the equation in line 10, you'll notice we have KD3 multiplying the first term and the second term. That's what's causing the problem. So we only can have KD3 once. So we're going to need to, because that's the rate. So we're going to need to get rid of one of those KD3s. There we go. Now run it. There we go.
okay.
Right? Because KD3 is the total rate of production. And so that should only be multiplying our Hill functions once. If we multiply them twice, then we have KD3 squared, which doesn't make sense. We have a rate squared. Okay, so there you go. So that's a, and that is a pulse generator.
Okay.
Let's see. So we see something that looks like that. Now the time scales over which these things happen are going to depend on those values of KD3 and KD23 and KD13. So we can play a little bit. But essentially what's happening is the following. P1 turns on P3 initially. It also starts producing P2, but initially P2 is low, so the inhibitor isn't doing anything. And then starting at time here, about 80, P2 gets to be bigger than half, and so it now turns off P3. So the direct route turns P3 on, and then the slowly developing P2 eventually turns P3 back off. So it's a pulse generator. And so that you could think of as potentially a functional circuit. It takes a steady state and turns it into something that's a pulse. And there are a lot of biological situations in which that's a functional thing. You have something that turns on. You don't want that to produce a signal forever. You want it to produce a signal that says it happened and then go away again. You'll notice that if you turned P1 off again, everything would turn off after a while. Why don't you do that with an event? So why don't you go to, say, time 200 and have P1 go back to 0 and run it for a little longer and see what happens. What did it do?
So P1 and the P2. Wait, what uh how should this P1 P2 change?
Well, let's take a look. Let's see what you got. So
Okay. So initially P1 to P3.
capital.
Oh yeah, right.
Start with them all 0.
Yes. And
Right? So you change it to P1, right? Fine, that's fine. And now you could say at time 200, P1 equals 0. See what happens. You'll have to run to 400. So P3 stays off and P2 comes down again. Now the system is reset. If you turned P2, now if you turned P2 on again, I mean P1 on again, it'll have another pulse, right? So it takes time to reset, but you could now have, say, time 300, you could turn it back on. Yeah. Okay. Great. And you can play games with the time scales. If the turn on time is comparable to the turn off time, then it doesn't do very much. You get a partial pulse or no pulse at all. So it's important that the turn on time for the direct path be fast compared to everything else. And it also depends on the value of P1. If we don't bring P1 up to 1, if we make P1 0.25, then P3 never really turns on. P2 never really turns on. Nothing much happens. If we make it 0.75, this will happen, but it'll be slower. So maybe before we move on to the next thing, why don't you just try, instead of setting P1 up to 1, try running P1 equals 0.25 and then run it again for 0.5 and 0.75 and see what happens. If you make it 0.75, what you'll see is the pulses lasts longer, stays on longer. Takes longer to turn on and then it stays on for. See if that works.
If it's 0.25, it's not enough to turn P3 on.
Why don't we let's look at it together.
Yeah, sure.
Yeah, 0.25 shouldn't do anything. So let's see.
At this
Yeah,
0.25.
right.
This
So
is
nothing happens with 0.25. Let's try 0.5.
yeah, this is 0.5.
Yeah,
And this is 1.
right. So you notice that it's actually a little maybe a little bit counterintuitive if I've understood these figures right. Which is the one that's on top that you're pointing to at the moment?
Uh this one is the P1 to 1.
Right,
This one.
right. So you'll notice that P3 stays on longer when P1 is smaller,
Yes.
which might not be obvious, right?
Yeah, indeed.
I mean, if you think about it, I guess it is obvious, but actually, the having a smaller signal actually means that P3 stays on longer than you would expect, which I think is maybe a little bit counterintuitive. That could be used, for example, as a compensatory circuit, right? If if you want something to get a certain amount of something to happen, and the input signal is small, you might have to do it for longer. So this is a circuit that could be used to adapt uh, to complex environments. Actually, that's probably one I should have discussed in more detail. I don't have a slide that shows the results of that in my lecture. Now, why don't we try the opposite one, which is suppose P1 inhibits P2 and P2 and activates P3. So this is also an incoherent feed-forward network. The net effect is similar, but is the time behavior the same or not?
Okay.
So in principle, we just have to change the the P to a K in the numerator for
Mhm.
P1 to P2, and the K to a P in the numerator for P2 to P3. See what happens. Now there is an issue here, which is we're ANDing the signal from P2 and P1 here at P3. But if you have a coherent signal where the activator and activator, you might want to OR it rather than AND it. But let's stick with an AND for the moment. What happened when you did that?
Yeah, I can share the screen
Great.
here.
So let's see what happens. P1 goes on. P2 does nothing because it's on. P3 stays off. Now I've turned P1 off. Then P2 comes up. That turns P3 on. And when I turn P1 on again, it turns off. So in this case, you might want to start with P2 equal to 1.
Yes, yes.
Maybe it's a little more interesting. Yeah, there we go. So here, P1, P2 starts turning off. By the time P2 is okay, why does P3 not come up? That's what I'm puzzled by. It comes up a bit, but not a lot. Now on the second phase, after you pulse it, it does. And that's because we're using an and instead of a. No, I'm trying to see. It should still, P3 should turn on. So let's see what we do. What is funny here? Um, Probably in this case, the issue is the time scales that we've used
At the beginning, the time is not enough for P3 to,
to turn on. Yeah.
yes, it's only
And
one. Like,
right. That's right.
yeah.
And so in the case that I had here, what did I do? I used KD2 of 0.05, so I made KD2 a little bigger. Instead of 0.01, I made it 0.05. See what of that. And I made KD3 faster. So here,
Yeah, I changed the,
yeah, yeah. So yeah, so here you see P3 turns on. Well, turns on when P1 is off.
mhm.
When you turn P1 on, it turns off, and vice versa. Okay. So in this case, that inhibitor is dominating everything. Um, if you play with the timing, you can get it to do a pulse, but it's not as pretty a pulse as the one that we have with the other circuit. The turn on is slow. The turn off is slower with the circuit. So there are quite a few games you can play with this. I don't think for today we're going to have time to do all of it, but I wanted to at least have us play with a little bit. And it does tell you something to some extent about how how even a very simple circuit can have quite a variety of behaviors. Another thing that you can do, which you've already started with, really, because you've turned the input on and off a bit, is suppose that we had, for example, P1 not being constant. Now here you turn P1 from 0 to 1 and then back to 0 and then back to 1 again. Uh, uh, but one could try, for example, P1 is 0.5 plus 0.5 times sine of time over the period. And if you do that, then you can essentially get a filtered output as a function of the frequency. Now, this isn't as interesting as the one you've been doing for the project, where you have an input a signal that's periodic on the input signal, and because of the feedback, you're getting frequency locking. Here, you can't get frequency locking. The output is always going to be the frequency of the input. But You can have something where if the frequency of the perturbation of the P1 signal is too fast, the output never turns on. Or vice versa, if the frequency is too slow, the output never turns on, depending on how you set it up. And so uh, maybe we don't have to do these all, but you can. Here's some examples where I've got a periodic input signal. I've made P1 time varying. And in this case, um, when the frequency is high, P2 comes up and reaches a steady state. P3 never turns on. Um, as I lower the frequency, I see P2 turns on and P3 turns on. And in this case, if the frequency is too low, P3 doesn't turn on at all or turns on less. And so this is actually acting as a bandpass filter. If the frequency of perturbation is too fast, I don't turn on. If the frequency of oscillation is about right, I track. And if the frequency of oscillation is too small, I don't turn on either. Now that's all for that I1 circuit. You could run that for different circuits and see what happens. I've played around a fair amount with I1 and I4. I've never really played with I2 and I3 very much, so it might be interesting to do that. Okay. So why don't you do that a little bit? Why don't you pick um, one of these coherent feed-forward networks and one of the ones we haven't done. So maybe pick, know which one. Let's pick C2 and I2, for example, and play with them just a little bit. There are a number of possibilities here. For example, you could find a network where P3 is turned on if P1 is either small or big, but turns off when P3 is when P1 is in the middle. So that's one where it excludes the middle. Another one is the pulse generator that we just did, where when you turn P1 on, you get a pulse. Another one would be if P1 is on and you turn it low, sorry, P1 is off and you turn it to an intermediate value, it generates a pulse. And if you switch it to a low or high value, it gives a steady state. So there's some possible selections. Now, finding these isn't always trivial because you don't you have a couple of things to worry about. You have those rates, those KD2, KD3 rates, and also the K values, the capital Ks may need to be adjusted. But why don't you try just play with the C2 one and the I2 for a few minutes, and plot what happens for P1 on and off periodically, and make P1 go from 0 to 0.25, 0 to 0.50 to 1, and see how those two circuits behave. So just take 5 minutes and play with that a little bit.
Okay.
Okay, what did you find? Anything interesting?
Yeah, I can show you this.
Okay, let's see.
Two figures. This one is for I2.
Yeah.
Wait, which one is for I2? One of them is one for I2. I think this one is for I2. This one.
So let's see. So which one? Let's look at the one on the left. The one on the left, when the input signal is off, you get a pulse. When you turn the signal on, it goes off, turns off. When you turn the input signal off, you get a pulse. Okay. For the second one, it when the input signal is turned on, the output stays low, and when you turn it off, you get a pulse. So the second one fires a pulse whenever you turn off.
Mhm.
So that's interesting. Okay, which one was the one on the right?
C2 is the left figure and I2 is the right figure.
I2 is the right figure. Okay. All right. So again, there aren't that many things they can do. They could basically filter. I guess the only other thing you could play with is if you make P1 not go between 0 and 1, but go between 0.5 or 0 and 0.75. See what happens. So there, yeah, turning on I want P1 turns it off partly, but you don't have time for it to turn off all the way.
Mhm.
I guess if you slowed it down, it would eventually turn off all the way. So, well, it doesn't turn off completely. It almost turns off, but not quite. Okay. So there again, we in this class we're not going to have time to go through everything, but there are really quite a few interesting behaviors you can get without with a relatively simple circuit. And so I guess the moral here is that perhaps this kind of feed forward network shows up a lot because it has a lot of potentially different functions. So another thing that you could do, and it's worth trying this maybe just for the one you have, is to simulate it with a Gillespie solver instead of with the deterministic solver. See what that does. And that'll be the last exercise. And then I wanted to talk about a little bit of principles of modeling. So why don't you see what happens? Maybe it's better to go back to the I1 case uh, and solve it instead of using the simulate, use Gillespie. But to make it work, you're going to have to rescale the values of the k. Because if between 0 and 1 won't work, so you'll have to make k something like 5, capital K and something like 5, uh, and the input signal something like 5. because the Gillespie doesn't work for remember it's the number of molecules rather than the concentration. So it has to be a, a number bigger than one. Now, actually, this problem when I wrote it originally, I wasn't thinking of using Gillespie. I was actually using additive noise. But additive noise has some issues in tellurium antimony, and so I don't want to spend the time showing you how to do additive noise. There are random number generators you can use inside of tellurium antimony, but that's one of those things I guess we'll just have to leave as a, if you're interested, you can read about it, but we're not going to do it in class.
I think the number is too small for the simulation.
Okay, let's take a look. What happened? Which one are you doing? I1 or
Yes, wait,
oh,
which one? C1,
you
the first one.
C1. Okay, C1. Okay, let's take a look.
The Gillespie simulation.
Yeah, yeah.
Yeah, and
What did it do? Okay. So let's see what we're gonna have to change. Um, what our capital K's need to be 5.
all of them, both of
Yeah,
them.
yeah.
Yeah. Okay.
Because that sets the scale.
Mm.
Um, let's see what's happening here. Yeah, okay. Okay, so P1 turns on, P3 turns on partly, P2 doesn't do anything. That's odd.
Seems
Why don't
in
you, sorry, go
in
ahead.
in Gillespie simulation, seems I cannot configure the P1 value.
Yeah, I'm surprised by that. I don't know why P1 doesn't change. Oh, try, so Gillespie, normally you don't do the number of points. So the second Get rid of that second 1200. But that may actually be a bug. It may be that events don't work in Gillespie. It should be strange. Let's try that.
Still not working.
That's interesting. I wonder what. P1 turns on correctly. P2 starts and then fails. P3 basically turns on a little bit and stops. Let's see. Let's look at our parameter values. Maybe there's something we missed. Can you scroll up and let's look at the A1, ED3.2. Hmm. I'm actually puzzled why this one is not doing what we'd expect. I mean, the one that's puzzling me the most is P2. Because P2 should be a simple result here. And P2 is essentially going to point one as the one and then stopping. So why is it going to one? K1 is 5. Let's make K1 and K2 50 instead of 5. And let's make P1 go to 50 as well. There. See what happens. Yeah. Well, so now we're getting some fluctuations, but P2 and P3 are staying resolutely between 0 and 1. Uh, Wonder why. Let's see. And P1 is shutting off. So at 300, P1 is shutting off.
Mm.
So the issue there is that what is the problem with that? Oh, the issue there is the K1 and K2 probably need to be rescaled too. So you probably need to multiply K1 and K2 by 50.
The small K1
Lower K1 and K2, yeah.
50.
And if this doesn't work, I may, I may, I hate to to have the last exercise be one where it doesn't work, but oh, didn't like that. Zoom error. Okay. You back okay?
Uh, can you hear me?
Yep. Yep.
When I was running the program, it suddenly consumed all my memory, and the whole computer just crashed.
Oh, well, I guess we had too many. That Gillespie could do that. So I guess, uh, all right. Well, I guess we'll leave that one
Okay.
for. I'm puzzled because it shouldn't. Those we've done Gillespie before and it didn't do anything strange. So without the events, it shouldn't be that. It should that if we started with the simple pulse generator, so the one we did with the I1
Hmm.
for the parameter values we had. Why don't we try that one time? Just let's go back to the I1 one that we had where you did the pulse, and
Okay.
and let's switch that to Gillespie and see what happens. Don't change the numerical values to begin with. Keep it between 0 and 1. Then we'll rescale it gradually and make sure we don't make a mess.
Too much noise.
Okay, let's take a look. Okay, so now that's because we're limited between 0 and 1. So now let's make the K's, the capital K's, 5. Yeah. And then we'll switch 20. Okay, and run that. And you'll have to make the at line 26. You'll have to make you'll have to make the additional value P1 5 as well. Line 12. Also line 12.
Oh, yes, right. Still the same problem.
Yeah, P2 and P3 don't want to come above 1, which is a bit odd. The I guess again it would have to be K1 and K2, the line 17 and 18. So let's try making let me make those 5. See if that does it. There we go. So it's not very pretty, but okay. So that is work.
Okay.
Now, if we rescaled everything enough, we would come back to the what we had before. We'd come back to the initial.
Mhm.
Okay, so we only have a few minutes left. I wanted to talk for a minute about something which is more limited cases, which is really thinking about um, whether results make sense or not. And this is something that I often talk about a little bit earlier in the class. And it could also be something that we do essentially when we do hill functions, where we don't really know complete information, and we want to come up with a mathematical guess that's reasonable. And so we were just seeing that the results that we got from the simulation didn't make sense to us. And so this is limiting cases are really a kind of question, which is, can we constrain our models a little bit? And I'm not going to go through, I have a lot of slides on this. I'm not going to go through all of them, but I want to talk about them a little bit. Um, and to begin with, suppose I had a bunch of possible time series here. Um, we know that variables and rates should remain finite for finite parameter and time values. Um, so having the value diverge at time 0 doesn't really make sense. Um, of course, if we can write mathematics that diverges outside of the time we're looking at, but everything should stay finite during the times we look at. Um, for a lot of the things that we're dealing with, like chemical concentrations, um, the concentrations or the number of individuals, for example, or density should remain positive. So that could rule some things out as well. Of course, rates of reaction could go negative, um, and things like electrical potential could be positive or negative. And so we shouldn't have divergences, and in many cases, we know things need to stay positive. And so if we know that things are positive, then it could reduce the number of cases we need to consider. So, for example, if we know that at time 0, our parameter value is 0, our argument is 0, then the dependence on the parameter or the time has to either be positive or 0, because we're not allowed to go negative. So we're able to rule out cases where we would immediately have a negative value. if we're talking about something like the rate of a chemical reaction as a function of uh, a parameter, typically the rate law is monotonic in the parameter. At least simple rate laws are monotonic. Hill functions, Michaelis functions are monotonic. And so that would rule out a dependency that looks like that. And so if you're trying to write a rate law, um, and things have to stay well behaved and monotonic, there are not that many ways you can do it. Of course, if you have sequences of, if you're trying to put a whole sequence of things together into a single rate law, like our pulse generator, then things can be more complicated. And so it's always worth asking the question, what happens at infinity and what happens at zero? So in general, uh, if we're looking, for example, at time behavior, uh, we, of course, we can imagine extrapolating the population of the Earth and getting an infinite value at long times. But values of which have to stay positive uh, as we go to infinity either have to go to a finite value or they have to go to infinity. Those are our only two choices. So we have to think about that's something we can think about a little bit. We want our parameters, our responses to stay finite, uh, and typically to reach a steady state at infinity. And so, if we look at infinity, we can ask the question, well, what are the possible slopes at infinity? We could have a thing diverging positively, diverging negatively, a zero slope, positive slope, negative slope. Uh, we could have which of those are possible? Um, and if we think about it, suppose we have something that's simple like the value increases linearly in time, then we'd have uh, linearly increasing slope at infinity. We could have zero slope at infinity, we reach a steady state. Um, we could have a positive divergent slope at infinity, I suppose. But we can't have a decreasing value at infinity or a negatively diverging value at infinity. Doesn't make sense. And so if the value at infinity is positive, um, and we want the thing to be well behaved, then the slope at infinity has to be zero. We have to reach a steady state. If the value at infinity goes divergent, goes up continually, then the slope is either at infinity has to be positive or divergent. Those are our only choices. So we have some limits there. If the value at infinity is zero, then the only possibility is the slope of zero at infinity. And so we can rule out a lot of possibilities. Similarly, at zero, if the value at zero is zero, then the slope is either uh, zero or increasing because we're not allowed to go negative. If the value at zero is finite, then we can have increasing zero or decreasing slopes. And so what we should say is always when we're looking at these things, first look at what happens at the appropriate lower limit, zero usually, could be something else. And ask the question, is the value zero or finite? If the value is zero or finite, potentially infinite, could be decreasing infinity. What is the range of slopes that are allowed? And then similarly on the opposite side, on the positive side, for very large parameters or variables, is the value zero? non-zero, or infinite. So we have a set of values at zero, a set of values at infinity, a set of allowed slopes. And potentially there may be other things we know about the system which constrain us at other places too. But normally we know what happens. If there's no chemical, the rate of reaction has to be zero, for example. At infinite time, all of the chemical is used up, so the rate of reaction is zero, for example. And so we're always going to ask that question, at zero, or the appropriate lower limit, is the value zero, positive? Is the slope zero, positive, negative? At large values of the parameter, is the value zero, positive? Is the slope zero, positive? And sometimes we'll know something about second derivatives as well, though not always. If we have an allowed value that can be negative as well as positive, then we're not so constrained. And of course, if there's a chaotic or oscillatory dependence on parameters, we're also less strained. Although the amplitude of periodic or chaotic oscillations typically has this kind of property as well. And so really we can always ask a question by looking at the limits at zero and infinity. That can tell us, does the answer, first, does the functional form we're writing down make sense? And secondly, are the answers we're getting making sense? And it's surprisingly common to write mathematical models which don't make sense in this way. And so, as an example here, our Hill function, suppose that we know that the value is finite at zero and at infinity. It has a slope of zero at zero and a slope of zero at infinity. Well, we have to start with a line here, horizontal here, a line here, horizontal there. It's monotonic, and so we have to connect those two lines. The only way we can connect those two lines following those rules is a sigmoid. If we have a sigmoid, we have to ask, where is the position of inflection point? Because the slope has to increase and then decrease again. So where's the position of the inflection point? What's the slope at the inflection point? And that basically gives us the Hill function. Could also be a hyperbolic tangent, but that's about all. And so the constraint that the value is finite at zero and infinity, and the slope is zero at infinity, basically forces us to have it, and we're monotonic, basically forces us to have a Hill function. We could have something that's slightly different from a Hill function, but not by much. And so that was the example that we had there. Suppose that our value was zero or finite at zero, and our slope was non-zero at zero, and our value and our derivative was zero. Our value at zero, non-zero at infinity, and our slope is zero at infinity. Well, in those cases, we basically get a Michaelis function or exponential relaxation. There isn't really any other choice. And so, again, by looking at the values at zero and infinity and the slopes at zero and infinity, we can essentially constrain the class of functions that we need to use to evaluate. And so these are examples of those kinds of results. Michaelis function, exponential function, they look pretty similar. They're not going to make a terrible difference. And there are going to be some more of these, and I'm running out of time now, so I'm not going to take too much more time. You could imagine a finite or zero value and an infinite slope at zero. For example, something looks logarithmic. Finite value at infinity, zero slope at infinity. Inverse logarithm will have that property if you want it. finite slope at zero, uh, zero slope at infinity, infinite value at infinity. Um, you could get something like x to the 1/2 will work for that, uh, or increasing logarithm will work for that. So there's another one that we haven't looked at, which was a zero value, zero slope at zero, infinite value and increasing slope at infinity. Uh, that's what's called an unbalanced Hill function. One can build those as well. And again, zero or finite value, zero slope at zero, infinite value, infinite slope at infinity. Uh, Power laws will do that. And so, uh, again, I don't have time to spend a lot of time going over all these details, but I think it's worth thinking about what are the reasonable, because very often when we start doing biology and physics, we believe that we have actual exact mathematical relationships. In biology, everything is phenomenological, and usually they're not measured very well. And so, if we want to write a rate law, um, our first approach to a rate law may be we have no idea what the rate law should be. On the other hand, we pretty often have a pretty good example, like the rate of chemical reaction should be zero if there's none of one of the substrates. Or at very high concentrations, the rate should be finite, or maybe the rate diverges at infinity. And in those cases, we can come up with reasonable approximations, functional forms, without having to know the exact structure. Uh, and they're not exactly the same, but here's an example. Here's f of x is x plus 1 cubed minus 1. Here's f of x is equal to e to the x. They're not exactly the same, but they're very close. Here's x cubed, here's e to the x minus x. Again, they're not exactly the same, but they're very close. And what this is telling us is provided we get the value and slope at zero and the value and slope at infinity right, we don't have to care that much about what happens in the middle. Uh, I'm not going to do the cases where you have divergence. There are a bunch of other possibilities. Um, but I'm going to jump ahead and maybe end with a bit of, for non-monotonic ones, there are more examples. I'm not going to jump through do all of those. We're out of time. But there are all sorts of functions one can write. But I'm actually going to end with this joke from the famous comic strip, which is this is what you call semi-quantitative thinking. And I say that we'll see this cartoon again, but this is usually I give this lecture earlier in the course.
I've seen this before.
You have?
Yes.
Uh, well, did I show this to you?
No, no, no. It's from a famous cartoon website. Uh,
Yes.
yes.
Uh, but what was the context in which you saw this figure before?
Oh, I followed that website.
Oh, so you just read it.
Yes, yes, I just read it.
But you see, I've made the argument that by by looking at the limits at the points at zero and infinity, we can guess what happens in the middle. And this particular cartoon is saying, well, maybe not.
Hmm.
Uh, so this approach, which is to use uh, theoretical reasoning about what's reasonable, only works if we have a pretty good reason to believe that we understand uh, the behavior that we're trying to model. In the case of chemical rate laws, we it's not unreasonable to think that the rate of reaction should increase when we increase the amount of each component. Uh, there should be no reaction when there's one of the components is missing. Um, the rate of transcription should have a basal rate of transcription and it should increase if the transcription factor is present. The rate of transcription can't get to be too high because you're limited by the rate of the polymerase. So those kind of arguments from the physical limitations of the system uh, mean that you can't be quite as free as they are here in the cartoon with coming up with the thing that you want. So I thought maybe I did want to end the lecture today with a little bit of humor. Did you have any questions about the project?
Yeah, still, the sorry, the presentation should be the still on Tuesday the same time next
If
week.
that, yes.
Okay, okay, sure. No,
And
no other questions.
and if that's, 20 minutes, half an hour, is that all right?
Not as long as half an hour. I think 15 minutes or 20 minutes.
Okay, that's fine.
Yeah.
I mean, my experience in the past has been usually it it winds up being harder for people to talk shorter amounts of time, but you decide what's reasonable for you. Okay.
Okay, okay, okay.
Um, it would be nice if you'd explain the papers a little bit, in addition to showing
Okay,
what you did, to show a few slides from the papers to explain, to show that you read the paper and that you understood what the paper was about.
okay, okay.
I mean, it doesn't have to be it doesn't have to be a research talk on the paper, but at least a slide or two to explain the
Mm,
context and the background of mathematics would be helpful.
okay.
Okay. All right. Anything else before we break for today?
No, no.
Okay. Okay. Well, I appreciate your patience. I'm sorry we didn't get the stochastic one to work first time off.
No.
Uh, I appreciate your patience with that. Appreciate it. And I don't understand what happened with that with the switching with the events in the Gillespie solver. I'm going to have to go back and play with that a bit myself to understand why the event handler wasn't doing what I expected.
Hmm.
Okay, well, if you want to meet before next week, let me know and I'll do my best to set up a meeting time.
Okay.
And look forward to seeing what you're able to come up with for next week. Thanks very much.
Thank you. See
Okay,
you.
good night.